video is designed to be watched after you watch the first shell method video. In this video, we are going to talk about um, rotating around something other than the y-axis or the x-axis. We are going to start with one that is over the x or y-axis. We're going to talk about rotating over something other than that, and then we are also going to talk about when might it be better to use the disc or washer method, because sometimes it is actually better to use that disc or washer method, and so we're going to talk about all of those things in this video. So our objective today is to find the volume of a solid of revolution using the shell method, and then to compare the uses of the disc and washer method and the shell method. Now, the first image that I have on here is actually just from our textbook, and this is so that you know what a shell looks like. So a shell is a hollowed out cylinder. The next image that I have on here is how shells help us find volume. And if you look and you have this equation y equals f of x, and the equation is the orange line, if we want to rotate this around the y-axis, we can take these rectangles and we can rotate them around, creating this cylindrical shell. Now, the width that you draw this rectangle is going to be the width of the shell, because that is what's being rotated around. And if you stack infinite number of these shells, if we were to draw a rectangle here and here and here and here, if you were to stack infinite of those shells inside each other, you will get the shape of when you revolve around here, and that's going to give you the volume. So the shell method is just another method to find the volume of a revolution. So the next image I really like, because this shows us if we were to take a cut out of some volume, out of some solid shape, this is what it looks like using that shell method. And you would notice that the smaller we make the width, the smaller we make our rectangles, the more accurate that volume is going to be. But what happens is we are just stacking these cylinders inside of each other to create the total volume. So how do we find the volume of one of those cylinders? Because in order to find the total volume, we need to find a volume of each individual cylinder and then add them up. So to find the volume of a cylinder, you're going to take the circumference and you're going to multiply it by the height, and that's going to give you the surface area of that shell. That's only two dimensions. That's only an area so far. That's the surface area, the outside region of that shell. How do we find volume? Well, you need that third dimension, and the third dimension is the width. It's the width. And in calculus, we are going to call that width either dx or dy, depending on how we're rotating. So a couple of formulas. The first formula that we are going to look at is going to be a horizontal axis of revolution, so revolving around the x-axis, for example. So if you have a horizontal axis of revolution, and you want to find the volume of this shape, you are going to draw your rectangles parallel to the axis of revolution. So parallel to the axis of revolution is going to look like this. Let me find my pen here. So parallel to the axis of revolution, we are going to have a rectangle that looks like this. And that rectangle then is going to get spun around, and we are going to make a cylinder like this. And of course, we're going to make infinite of these cylinders to stack inside of each other. So in order to find the volume of this, we need to find the circumference. And the circumference is 2 pi r. So here's the 2 pi r piece of that, 2 pi r. And you will see that this is in terms of y. It's in terms of y because the width is in terms of y. That's going to be dy. And you're going to see that there. So that's the width. So this piece is the circumference. This piece is the width. And then this is the height. Because when you put all of this together, that's going to be the surface area. And we found on the previous slide that surface area times the width is going to give us the entire volume of that shell. The height of this is going to be the distance from the axis of revolution to that outside edge. And the distance from the axis of revolution to that outside edge is just y here. Okay, so that is how we would find the volume using the shell method. Now, what if we want to rotate vertically? So vertical axis of revolution, here we go. We're going to take this right here and we are going to rotate it like this. And every single time you draw your rectangles, you're going to draw them parallel to the axis of revolution. So parallel to the axis of revolution, it's going to look like that there. And then we're going to spin this around and we are going to make, I don't know why that disappeared. And then we're going to make a cylinder like this. Um, and so again, to find the volume of the cylinder, we need to find the circumference, which is 2 pi r. We need to find the height, which is going to be h of x. That gives us the surface area. And if we multiply the surface area by the width, we get that volume, and this is the width right here. So whenever you're drawing rectangles that are vertical, it's going to be in terms of x. Whenever you're drawing rectangles that are horizontal, it's going to be in terms of y. So one big thing to remember whenever using the shell method is you are always going to draw your rectangles parallel to the axis of revolution. So parallel to that axis of revolution. Okay, let's put these into play. Let's actually practice this. Let's use a shell method. Okay, so we are going to use the shell method to set up and evaluate the integral that gives the volume of the solid generated by revolving the plane region about the y-axis. And then here are our equations. Y equals 1/2 x cubed, y equals 0, and x equals 3. And the first step is always to draw, so to graph. I'm trying to find my cursor here. So always graph first. And that's going to allow you to see what is the region that I'm rotating, because the region helps you figure out what shape you're going to make. So let's go ahead and take a moment to graph. So I really like to use Desmos. I like to use Desmos because, well, if you have internet access, then it's completely free. It also does a lot of the same things, if not more, than the graphing calculator, and it's very user friendly. So in black, I've graphed 1/2 x cubed. In red, I've graphed y equals 0, and in blue, I've graphed x equals 3. And you will see those 3 points where they intersect, and those 3 points where they intersect is going to be the region that we're talking about. And so the region specifically that we are going to be rotating around is going to be right here. It's going to be right here, and sometimes it's hard to see that, and that's why I like to graph all of the lines. And so those were all of our lines like this. So that's the region, and it said we're going to rotate it around the y-axis. So rotating it around the y-axis, I am not very good at drawing with this, so bear with me as I try my best to draw this shape. So you're going to have the cylinder outside. Okay, so we have that cylinder outside, and that comes from rotating this piece around, because that piece, as you rotate it around, is going to stay in the same, it's not going to stay in the same spot, but it's going to stay the same distance away, which is 3. So it's always going to be 3 away from the axis of revolution. And now I need to spin this one around. Let me try changing colors just so that it's easier to see. So now when I spin that one around, that's going to make like this hollowed out bowl here. So our shape is going to look something like that. Now, Using the Disker washer method, we definitely have to use washers because we have this hollowed out portion here. We are finding the volume of everything on the outside, and then we're hollowing out that bowl. And so we certainly could set up washers here. We would be cutting washers in this direction, and so we'd be doing it in terms of dy. Um, if we were to use the shell method, we would be cutting rectangles in this direction. Let me just draw it on the graph here. Our rectangles are going to go in this direction here, which means everything is going to be in terms of x. Well, everything's already in terms of x. So if I use the shell method, I don't have to rearrange anything. I don't have to put things in terms of y. And so the shell method might be a little bit easier here. So let's try it out. The shell method states that if we are going to do a vertical axis of rotation, we're going to do 2 pi, because we have to find the circumference, from a to b of r of x, because remember this piece is the circumference, it's the circumference here. We need to multiply it by the height of our rectangles, which is this piece here, and then we need to multiply it by the width. So we need to figure out what is r of x and what is h of x. So r of x is going to be from the axis of rotation to the outside, right? Because that's going to be half of the diameter. And so that's this distance here. Well, that distance there is just x. It's changing depending on where we put our rectangles, and so that distance is x. So r of x, I'm going to replace with an x. So let me rewrite this 2 pi, and then r of x is just x. H of x is our height, so how high up is this rectangle going? And that is going to be equivalent to our equation. And our equation is 1/2 x cubed. So I'm going to replace that h of x with 1/2 x cubed, and then our width is dx. Now we need to figure out our bounds. We are integrating with respect to x, and so we want to know what is our lowest x value for this region and what is our highest x value for the region that we're rotating around. So our lowest x value is 0 and our highest x value for the region that we're rotating around is 3. So we're going to go from 0 to 3. Now we can integrate this by hand. It's not too hard. We're going to distribute in this x. So I'm going to write up here so I have a little bit more room. So we're going to have 2 pi integral from 0 to 3, and then this is going to be 1/2 x to the 4th dx. When you integrate, you are going to increase your exponent by 1, and then you're going to divide by that, and so we're going to have 2 pi. And increasing this by 1 is going to make it 5, and then dividing by 5 is going to make this 1/10. So we have 1/10 x to the 5th. Because we took the integral, the dx is dealt with, it's done, and so we're going to go from 0 to 3. Now we have to plug in our values, so we're going to have 2 pi, and then we're going to plug in 3, because you always plug in your upper bound first. So 3/5 over, or not 3/5, oh my gosh, I'm so sorry, 3 to the 5th power over 10, and then we're going to subtract 0 to the 5th power over 10. This is just 0. 3 to the power of 5 is 243. So this is 2 pi times 243 over 10, but I can reduce the 2 pi and the 10, so that becomes pi over 5. So this is 243 pi over 5. Now, any definite integral, meaning it has a lower and upper bound, any definite integral you can also solve using technology. And so let's see how we would plug this into Desmos. To plug it into Desmos, I'm not going to put the pi in there because that's irrational. So I'll put the 2 and then I'll add the pi later by hand. And I'm going to integrate from 0 to 3. I'm going to put x times 1/2 x cubed dx. and then it solved it for me, 48.6. I clicked on this button here because that turns it into a fraction, and I got 243 over 5, and we multiplied by pi. So you can multiply this out using technology, or you can do it by hand. So we just found the volume of this, and we did that volume without having to set up two separate integrals. And that's the beautiful thing about the shell method, is that these washers that we used to have to do two separate integrals for, we no longer have to. And that is pretty cool. That's pretty cool. Um, so yeah, let's try another practice here. Okay, so in this practice, we're going to talk about a pontoon. A pontoon is to be made in the shape shown in figure 6.34. That figure's coming up shortly, don't worry. The pontoon is designed by rotating the graph of y equals 1 minus x squared over 16, using this domain, -4 to 4, about the x-axis, where x and y are measured in feet. Find the volume of the pontoon. And I'm just thinking, what is a pontoon? And I Googled it, and Google said it's just something that's buoyant. Sometimes it's a boat for military purposes, sometimes it's a buoy, anything buoyant. So this is what figure 6.34 looks like. This is our pontoon, and we want to find the volume of this pontoon. So as always, my first step is going to be to graph. Let's graph this so that we can see exactly what it looks like using our equations. So here we go. We are going to type in y equals 1 minus x squared, oops, over 16. And we're going to put the domain from -4 to 4. If you don't know how to put the domain into Desmos, you use these squiggly braces. Then we're going to zoom in, and this is what our graph looks like. And so we're looking at the region that's bounded by the x-axis because we're rotating around the x-axis. So this is what we're looking at right here. And the graph looks like this. So we are going to be rotating this piece of it around the x-axis like this. And it's going to make this shape here. So right now, we're in the position where we need to decide which method are we going to use and why. So if we were to use the shell method, because that's what we've been talking about, we would be cutting rectangles like this. We'd be cutting rectangles like this, and then we'd be doing in terms of dy. So we'd be doing in terms of dy, which means that everything has to be in terms of y, which is not impossible to do. Sometimes it'll be impossible to do, but it ends up being a square root function, and it ends up being the positive and the negative piece of that square root function. And so in this case here, I think it's going to be a little bit ugly to use the shell method. So for me, instead, I think that we should use the disk method, because if we were to use the disk method, instead of making our rectangles horizontally, we would make our rectangles vertically. And when we make our rectangles vertically, we're going to do things in terms of dx. So what we're going to be doing is we are going to be taking cuts from this like this, and it's going to look like that. So we need to remember, how do we do the disk method? So the disk method, what we're doing is we're taking cylinders or disks, and they're looking like this, and then we have to find the volume of those disks. Well, the volume of the disk, well, we need to find the area of the circle, and the area of the circle is pi r squared. And then to make it a volume, we need that third dimension. That's going to be the dx piece of it. That's going to be the width. And because we have a dx, we know we're going to need to integrate. So we are going to be integrating from a to b of pi r squared dx. And of course, pi is a constant, so you can put him out in front. So we're going to be integrating pi times the integral from a to b of r squared dx. So we need to figure out, what is r? What is the radius? What is the radius from here to here, or from here to here, or from here to here? We need to know what the radius of this pontoon is. Well, the radius is coming from that equation. And because we are integrating with respect to x, we want our equation to be in terms of x, which it is right here. So we're going to be integrating the equation 1 minus x squared over 16 squared dx. We need to find our lower and our upper bounds. And so we're twisting this whole piece around. And so this is going to be our lower and this is going to be our upper. So we're going to be integrating from -4 to 4. Now, we certainly could solve this by hand. We would have to do a binomial expansion, and then we could integrate using the power property. For this particular case, I'm just going to go straight to Desmos because it's a definite integral, and I'm going to have Desmos do it for me. So using Desmos, I think I'm going to end up putting pi in here, but I'll wait until the end. I will put pi because we are estimating an actual volume in feet. So 1 minus x squared over 16 squared dx. And we get 4.26 pi, or 64 pi over 15. But because this is an actual volume measured in feet, I'm going to put the pi in there and I'm just going to round it. I'm going to round it to 13.4 feet cubed. This is 13.4 feet cubed. So our actual answer here is 13.4 feet cubed. All right. So that was an example where we had to decide which method was going to be best. You could have done it using the shell method. If you want additional practice using the shell method, now that you know what the answer is, pause this video, work it out using the shell method just to see that you will get the same answer, but you'll see that it's a little bit more work. Okay. In our next practice problem, we are going to rotate around something that's not the x-axis or the y-axis. So we're going to find the volume of the solid form by revolving the region bounded by the graphs y equals x cubed plus x plus 1, y equals 1, and x equals 1. About the line x equals 2, this is not the x-axis or the y-axis, which makes this a little bit more tricky. But of course, our first step should be to graph. So let's go ahead and see what this looks like. We're going to put in the first equation, which is x cubed plus x plus 1. And then our second equation is y equals 1. And our third equation is x equals 1. And then in a dashed line, I'm going to put in x equals 2. So if you hold the line, you can change it into different color or different type of line. And so I put a dash because that allows us to see what we're rotating over. Now, the other thing that you'll see is I am clicking on the points of intersection because that is where we are going to actually rotate around. So yeah, right now I'm just restricting my domain so that I can see that actual region and just that region. So here's the shape. This is the shape that we are going to rotate around this line here. A couple of things I want you to notice is this is not exactly on the x-axis, and so we have to keep in mind that we are not finding any of the volume here. And then this is all going to be empty here. Now, I'm not super great at drawing with this thing, so bear with me as I try to draw out this shape. So we are going to kind of have the base of a rocket. So this line is going to swing around, staying this far away. This is going to swing this way. You can kind of start to see this come to life as the base of a rocket. Um, and then this piece, let's get a different color because that line's in green. Maybe let's use green. Um, this line is also going to swing around. And so it's going to be like this. Oh, I guess that should be, oops. I'm really sorry. I'm not great at drawing this on here. And then this will swing around and be the back side of it. And because this is the region here, everything on the outside is really what we're solving for. We're solving for all of this area, and that blue cylinder on the inside is what's hollowed out. Um, so we could definitely find this using the washer method. Using the washer method, we would cut discs like this, and again, it would be in terms of dy. And so we would need to rewrite this in terms of dy, or in terms of y. And honestly, I think that's a nightmare because we have multiple terms um, with different degrees. It would be a nightmare to try to rewrite that in terms of y and get that x alone. So in this case, the shell method is really your best option because by using the shell method, we are going to take cuts like this, and they are going to be parallel to our axis of rotation. Oops, pretend like that's better. And then we're going to swing that around. We're going to swing that around to make these shells. That was a little higher than I wanted it to be. I'm sorry. So there's a shell, and we're going to find the volume, and it's got to be a little thick because I drew the rectangle thick. We're going to find the volume of this shell. And so to find the volume of this shell, we need to know the width. Well, the width is in terms of x because we do our rectangles like this. We need to know the radius. The radius is a little bit different. We know that the distance from here to here is x. But that's not the radius of this because we are not rotating here, we're rotating here. The radius of this is actually going to be from here to our equation. So from here to our equation, well, what number is this? This number is 2. This number is 2 because we're rotating around the line 2. And this is x, so it's going to be 2 minus x. Our radius is going to be 2 minus x. If you need to take a moment and pause the video so you can soak that in where that just came from, go ahead. But what we did was we took our axis of rotation and we subtracted x from it to get to that point on our line. Now we need to know the height. Well, the height is pretty straightforward, except we're ignoring all of this space here. So we want to subtract that from the end. We want to subtract that from the end because we want the region that's bounded between y equals 1 and the line. And so we're going to subtract this y equals 1. We're going to take this area away from this line. And so our height is going to be the equation in terms of x minus that bound, that y equals 1 bound. So now we have enough information to set up this integral. So remember, when we're trying to find the volume using the shell method, we're going to do 2 pi r times our height times our width. So 2 pi r, so we have 2 pi, we have to figure out what we're going to integrate from, and then r is 2 minus x. Our height is this equation here, so x cubed plus x plus 1 minus 1. And then our width is dx. And we need to figure out what are we integrating from what to what. Well, the region this is the region. I know it's starting to get a little messy. What is our lowest x value and what is our highest x value of the region that we're rotating around? Well, the highest x value is 0, and the lowest x value is 0, and the highest x value is 1. So we're going to integrate from 0 to 1. Now, we could multiply this in, and we could do all of this by hand. If you're planning on taking the AP test, you should pause this video and you should do that for additional practice. But here, I'm going to use Desmos to solve this for us. So using Desmos, I'm going to plug in the 2 out front. I'm going to leave the pi out and add that later. I'm going to integrate from 0 to 1. And then it's going to be from our radius, which is 2 minus x. We're going to multiply that by the height, which is x cubed plus x plus 1. And then we have to subtract that 1 from that y bound dx. Now, you don't normally see the subtracting piece of it because most of the examples that we've done, we have bounded with y equals 0. But in this case we aren't. So 29 over 15, but remember I didn't put the pi there. So our final answer is actually 29 pi over 15. That was a lot of work. There were a lot of components in there we had to think about. We had to think about, well, we're not rotating over the x or y axis, so how does that 2 come into play? We had to think about, well, this was not bounded by y equals 0, it was bounded by y equals 1. How did that come into play? And all of those pieces helped us to solve the volume of this little base of a rocket. Okay, I have one more practice to do with you guys, and it's going to be another one where we're rotating over something other than um, that axis. So use the shell method to find the volume of the solid generated by revolving the plane region about the given line. And we have these 3 equations here, which is y equals the square root of x, y equals 0, and x equals 4. And we're going to rotate about the line x equals 6. And of course, our first step is to graph it. So let's see what this graph looks like. We know what y equals the square root of x looks like, but I love just graphing it so that I can get a really good visual representation. This time we are bounding by y equals 0, so that's not going to hurt us. And then we have x equals 4. That x equals 6, I'm going to put as a dashed line so that we can see where we're at. And then you'll see that I'm going to go through and I'm just going to restrict all of my domains so that I can really clearly see what region we are rotating. So what I'm doing right now is I'm figuring out what is my range, because to restrict the x equals, I need to put in my range. All right, so the region that we are rotating is this one right here. So we're rotating this around x equals 6. So we are, again, where's my pen at? Sometimes I click buttons on my pen and then it turns off and it makes me a little sad. So we are rotating this direction around here. So this piece is going to be like this. And I did not make enough room on here. It's going to go all the way out like that. This center piece is going to be hollow. The center piece is going to be hollow. And so that center piece is going to be a cylinder like this that's hollowed out. You can see this start to come to life a little bit. This piece is going to be rotated around. So it's going to look something like this. And that should be perfect distance. It really should be a heck of a lot bigger than that because of the sheer distance it is. But it's going to look something like that. And then, of course, the region that we were rotating is this one here. And so the whole outside of this is going to be what is shaded in. That is the volume that we are finding there. Um, so again, we definitely could use the washer method, and in this case, the washer method wouldn't be so bad because it's really easy to isolate our x and get things in terms of y. You'd have to get things in terms of y if you're doing the washer method because you're going to cut like this and make cylinders that direction. But let's practice using the shell method because then we don't have to do more than one integral here. Um, we're not finding an inner radius and outer radius. And so in order to do the shell method, we are going to make cuts maybe like this, rectangles like that, and we'd be rotating that around. So that rectangle would go something like here, and then it would be a cylindrical shell with that thickness. I really like those images in the front because I'm not very good at drawing these, so I think the images in the very beginning of this slideshow helped show what these shells look like. So we are creating a shell like that, and the thickness of it is dx because they're vertical. So dx is going to be the thickness or the width, and then our height is going to be the equation because we are going all the way down to 0 this time. So it is just the equation. We don't have to subtract anything from it. So y equals the square root of x is our height, and then the radius is a little bit more challenging. Now we know that um, from the y-axis over to here is x. So from here to here would be 6 minus x. And you might start to see a pattern here where it's always this axis of rotation if we're doing it vertically minus x. So you might start to see that pattern, which is pretty cool. So now we have enough information to set up this integral, and the integral is going to be, remember, you have to have the circumference on the outside, so, or not on, I'm sorry, you have to start with the circumference. My phone is blowing up right now, and so I had to throw it to the side. Times the radius, which is going to be 6 minus x, and then times the height, which is the square root of x, times the width, which is dx. And we need to figure out what we're integrating from, and how to figure what you're integrating from is just the region that is being rotated. So the region that is being rotated is this, and our lowest x value is 0, and our highest x value is 4. So we are integrating from 0 to 4. We definitely could integrate this by hand if we wanted to. We need to distribute this in and then use the power property of integration. But let's go ahead and use Desmos and integrate it. So again, I'm only going to put the 2 out front. I'm not going to put the pi because pi is irrational, and I'll just add that later. I'm going to go from 0 to 4. I'm going to put my radius here, which is 6 minus x. And then I'm going to put the square root of x. And then dx. And I get 38.4, and of course I can put that into fraction form by clicking here, and I get 192 pi over 5. So this volume is 192 pi over 5. And because it's volume, we'll put units cubed. Okay, so that was pretty nice. Not too hard. The more practice you get at figuring out what is my radius, what is my height, the easier this gets. I personally like the shell method because for me, you don't have to set up what is the inner radius, what is the outer radius when you're doing the washer. So whenever I have one of these hollowed out regions, I personally like to use this shell method. All right, so here are some problems that I would like you guys to work on for additional practice: 23, 25, 31, and 33. And as always, I just assign the odds so that you can go on to Calc Check to check your work. I hope you found this video helpful.